Evening, everybody. So welcome to the DynamoDB Streams and cross-region replication talk. I know it's probably been a long work day for you guys, so I'll try to make this short. And as Steve said, put your hand up. We have a pretty small, intimate crowd here today, so I'd like to be interrupted more if you have any questions during the presentation. The presentation itself should only take about 20 to 30 minutes, including the live demo at the end, which should be hopefully very fun for everybody. So again, if you have questions are good, keep asking. I'm going to pause also at different intervals to make sure that people understand. But before I start, there's a bit of fundamentals of DynamoDB. I just want like a quick show of hands. You know what NoSQL is, have worked with a little bit before, know what Dynamo. Okay, so very good crowd. I'm going to rush a little bit through the beginnings of NoSQL because there's just a few slides I threw in there just in case not everybody was on the same page. So quick overview, we'll go through a bit of motivations, basics of DynamoDB. I want to focus a lot of the presentation on how streams actually works for DynamoDB, how consuming streams is a challenge sometimes, the differences between AWS Lambda, advantages of using either AWS Lambda or Kinesis client library to consume DynamoDB streams, and finally the demo on building an actual application, which is cross-region replication on top of it. I'm not going to spend too much time. There's obviously a bunch of advantages moving to a NoSQL, especially under the AWS ecosystem, fully managed. You get a lot of consistency, availability, durability guarantees. Quick review of the data model. In DynamoDB, there's no instance that you connect to. You basically go to the console or use our APIs, use our SDKs, create a table, and then you can immediately start writing data to it. The table, we call it a table. It's really like a gigantic document. The way that it's displayed here is just, I can fit it on my slides better. But you can think of each row as sort of like one document, and then each document itself can have sub-elements, what we call attributes. So in this case, there are 2 items or documents, and each item has a number of attributes. The first one has 4, the second one has 3 attributes. So it's not required that you have an attribute for each single item, except the primary key. So you can have an attribute that you define as the key for your table, and this attribute must be present for every single item in the table. In this case, it's called record ID. There's another case where you want to have 2 attributes as the primary key, and that's a hash range key. A lot of this is very well documented on our official documentation. I want to talk a little bit of partitions, a very important concept in DynamoDB. It's how we do horizontal scaling. In this case, you have tables and you have items inside the tables. We take your hash key value. In this case, the hash key is record ID. Then we hash it into some random value in the key space, and then we place it on disk. And as your table gets more and more items or more throughput, we need to scale out in order to maintain performance. Or optimize for performance, and that's just more and more partitions. So as your table grows, you can expect the number of partitions in your table to grow with it. And this is a very important concept because I'm going to start talking about DynamoDB Streams. Okay, so that was the foundation of DynamoDB. Questions? Anybody not clear? Yeah? Yeah.
So essentially, DynamoDB is kind of like MongoDB in that you have a document, you have attributes or key value pairs, and not every document has to have the same attribute. Can you build I apologize if I'm asking about DynamoDB. Can you build indexes on other
Yes, you can.
Basically?
Yes, you can. Yeah, that's covered extensively on our documentation. But what you mentioned for sure, MongoDB, also another NoSQL database, I think this, like not having the same attribute for every item and thinking of it as a document is a fundamental principle that applies across all NoSQL databases. Yeah, Go, you had a question?
Yeah, when you increase the partitions, the item that lands on, so the record 1 used to be on the partition 1, or let's say record 3 used to be on the partition 3, but if you continue increasing it, it lands on different partitions.
Yeah, so in this case, if the third partition splits into 2 partitions, that's usually how we split it in 2s. It will land in one of the partitions, and the original partition would basically be an inactive. So what happens is right now the key space is divided between AA and FF. Depending on where the hash is, it'll land on either the first half or the second half, and that will keep splitting. So it'll always land in one of the what we call children partitions, and the children partitions are going to be the only active partitions, and the parent partition would be made inactive. So basically, you think of it as splitting the key space. Okay, so I'm going to continue talking about DynamoDB Streams. So if you don't know what it is, it was a relatively new service. At least this slide is from like a few months ago. We went to general availability last year, actually. What it does is basically think of it as a stream of continuous pipeline that records what happens to your table. In today's world, we only have 3 write operations to DynamoDB. That's put item, so inserting a new item, updating an existing item, and delete item. So you can get 3 types of you can think of it as records in this log. And the log just says, you inserted an item, or you updated an item, you deleted an item. And this log has to scale similarly to how the table scales. The log has to scale also with table size and throughput, because your tables can have thousands of partitions, and your log needs to have some sort of a logical ordering. And I'll talk about that a little later. So let's look inside what a record looks like. Very simple example. We want to do an update to an existing item. Before the update, record ID equals to 1, name equals to Alice. We just want to change the name from Alice to Allison. So we do that, and afterwards, the record becomes record ID equals to 1, name equals to Allison. When you enable the stream on the table, you have to choose what view type you want. So this is like, when you enable the stream, you're going to say, I only want to see this view of the change log. So take the first one, for example. If I enabled the stream on this table, and I said I only want to see the old image, which means you'll only get the before update image for every single operation. So in this case, the record will only show you record equals to 1, name equals to Alice. And similarly, for example, if you had old and new image, you'd get 2 images per record. And that is the before update record and the before update image and the after update image. So we don't actually store the delta. We store the entire image, like what the item was. And in the case of, say, like a delete, before the delete, there was an item. After the delete, there's nothing. So old image would be the item, and new image would be null. And that's how we represent deletes, and inserts is vice versa, the reverse. Last case, keys only. Some of our customers, they just want to audit, like how many times did I write to a certain key, for instance. And they, for cost and performance reasons, they just choose keys only. So the event log only shows, you wrote to record 1 once, twice, etc. So this is in the details. I'm going back to the overview now. So I talked about partitions. In this case, we have a table with 3 partitions, 0, 1, and 2. And I want to talk about how the sharding in the stream works. So the entire big box on the right is the stream for this one table. Right now, the mapping is one partition maps to a whole lineage of shards. So that's like one row of shards. What I mean by a whole row of shards is at one time, the changes that happen to a partition won't be stored on a single shard in the stream. However, the shard, approximately 4 to 6 hours currently, the shard actually closes itself and opens a new one. So that future writes to the same partition will go to the new shard. So it's a lineage. If you think about it, in this case, we look at the top row, 0 was the oldest shard, 0 closed and 1 opened, and then the writes were going to 1, and then 1 closed and 2 opened, etc. So now we're on 4. So 4 is the only active shard in what we call a lineage. So what a lineage is, you have parent, and then you have child, and then you have children of that child, so grandchildren. And that's, I will go through this in a little bit more detail. But this is actually the sort of fundamental scaling principle behind streams, is we're able to create more shards so that it can keep serving data at the same latency. So let's look at it in a little bit more detail. The top one, so I've used dotted white lines to indicate the same lineage, right? So the top one forms one lineage. It's a simple lineage, so I want to go through that one first. So say you have an item that sits on partition 0, and we're updating this one item again and again. What happens is these updates will be recorded on the shard, starting from shard 0. Approximately 4 hours later, this shard will close. A new shard 1, will come up. And now updates to this partition will all go to 1. 0 is still there if you want to read from it, but it can no longer be written to. You can only write to one active shard at a time. This keeps going, and say it's been 4 times 5, so 5 hours. It's been 20 hours. Now it's writing to the latest open shard. We call a shard open and closed, and that's the number 4, shard number 4 up there. And this is an important concept because you have to follow the shard ordering in order to make sure that you follow correctness and consistency, right? Yeah, go.
Why do you close and then create a new shard?
So there's various reasons on the back end that this happens. Fundamentally, it's because once you have too much data on one shard, on the back end, it becomes very difficult to serve the performance with low latency. So we need to start with a new shard so you're not. This is just, like on the back end, there's dependencies, and this was something that was enforced in order to do this. The thing that I was talking about is with lineage, if you're updating a record, say you're incrementing something, and you're going 1, 2, 3, 4, 5, and it lands on different shards because you're doing this, say, over a few hours, you want to make sure you process a parent shard before you process its child, right? Because you want to make sure that you process it in time ordering. Otherwise, you're going to lose that ordering guarantee, and you're going to get random data like 1, 5, 2, 3. You're going to lose the consistency and the correctness in the data. And this becomes very important when you are thinking about how do I want to consume a shard. I want to make sure that I start from the oldest shard, and then I follow that ordering. So I have to find the child of the parent, process that child, then process its child, etc. In a more complicated example, I'm going to the second white box now. A partition can split. So in DynamoDB, partitions will split in order to keep, again, going back to the latency, throughput, performance. It can split down based on size or throughput. There's a lot of information out here, out on the web for DynamoDB, how partitions split and how to calculate how many partitions you have. Essentially, when a partition splits, its shards split as well. So in this case, partition 1 has its own lineage of shards, just like the first one. But it'll split into 2 child partitions, partition 2 and 3. And each of them will get its own lineage. So this is now interesting because an update that used to go to partition 1 into one of its shards now has to land in partition 2 or 3. So this goes back to what Go asked earlier. What happens to an item when it splits? It'll land in one of the 2 partitions, but not both. So it'll be one or the other. It'll be mutually exclusive, basically. And then in that case, all of its updates would be recorded in the corresponding shard lineage. So if an update went to, say, the shard lineage for partition 2, you will never see it in the other lineage. Again, very important when you're trying to track different items across time and space, and you want to make sure you process the records in the same order. So to summarize, yes?
So what about deletions? How does that work?
Deletions work the same way. So if you delete it from partition 1, then that record will show up in, say, the shard number 4 in its lineage. And later on, when the partition splits, it splits it based on key space. So the existing items also gets transferred onto partition 2 and 3. And depending on which item you delete, you might see a delete record show up in partition 2's lineage, or you might see a delete record show up in partition 3's lineage. Yeah?
So for the purpose of lineage, the zeros under the split partitions are considered children of the 4 under the original partition?
Yes, exactly. So if you think about it in this way, the top example, 0 is a parent of 1, 1 is a parent of 2. In this case, like you mentioned, in the bottom example, shard number 4 of partition 1 is a parent of both its children, which is zeros of the partition 2 and 3. So that's actually a good point. I should probably make a different diagram. So a parent shard now can have 2 children because the partition split into two partitions. So it causes 2 new shards to be created. Yes.
So how fast is the partition split? Like the question is basically, while you're splitting the partitions, you have writes, are the writes buffered until the partitions are done and then decide where the new records are gonna go, or how does that work?
So I don't know all the details, like the nuances. First of all, it definitely only shows up either once in the parent or once in one of the child. You won't see like the same record show up twice for sure, for correctness. In terms of whether it's buffered, I believe what happens in this case is they actually like add two partitions first. So the two partitions. Now, don't quote me on this, but I think how it works is that they're all in sync. Like all three partitions are in sync and receiving all the writes at the same time. And then at once, everything gets dropped. Like half of it gets dropped.
They're immediately available during partition time.
Yeah, there's no downtime. So when the split happens, depending on basically the short answer is there's no downtime. The long answer is sometimes you will receive like an internal server error, like a 500, but that should only be last maybe less than 2 seconds. And that's when like you happen to want to make a write, which has to go to the master, but at that moment the master is being transferred. That's why it has to last like less than 2 seconds. But we have like SLAs internally to monitor those metrics. Any more questions? Seems like there's a lot of interest on this slide. It's a little bit of a tricky concept, but I think it's interesting to understand because it's a classic distributed system problem. Yeah.
So if I want to traverse my records back in time, you read shard on the bottom example, shard 1, 0, 1, 2, 3, 4, and either shard 3 or shard 2, 0, 1, 2, 3. If I want to read
Yes.
sequentially in time.
Yes. So if you want to read, yeah, like you said, 0, 1, 2, 3, 4, and now you don't know where your item went depending on how it's split. So you have to read both zeros and both ones. Once you find it, then you can eliminate the other one because you know it's in this lineage for sure. So it'll stay in the same lineage. Yes, Steve?
How do you know, if that's one item, how do you know where it's going to end up 1 or 2 for the next record? Presumably you're tracing it to figure out where to start spooling to actually read from. You don't want to continually. Maybe your sample is going to show us how to demystify this, but is the expectation that the consumer will actually bounce between shards for streaming?
Yeah, so if you're tracking a specific record, most of our use cases, you're just processing batches of records, right? But if you're tracking a specific one, then you'd have to do what I said, which is you have to go to both children. And like I said, a shard lasts like 4 hours. So you probably find it in one of the shards in the first one. If not, and you're unlucky, then you have to go to the children for both shards to keep searching for it.
If you just want to stream in time, just the facts and time of the updates, is there a simplified model so that you can just get the actual next update in a stream? Or how does someone determine time?
So there's actually no time concept in streams currently. I don't know if it's coming. There's just a sequence number. That's
Sequence fine, yeah. I mean,
sure,
sequence
yeah.
Order,
Yeah.
Is there an easy way to track just next
Which branch it goes to?
or just sequence, just general like authoritative sequence across?
Yeah, so yeah, there's a monotonically increasing sequence number that'll tell you like this record came after this one. And then that's how we determine order. But there's no way to deterministically decide which shard it actually went to. Yeah.
Yeah, I have a question about that. Like, let's say you're writing a Lambda function that waits on the DynamoDB streams and pushes the records to firehose and maybe to S-Suite. And then you write your Lambda function such that you have each Lambda function for a suite. So what happens then if somehow your stream, your shard splits? How is your Lambda function?
Yeah, so I'll go through this in like 2 more slides-ish. Lambda actually hides all of this away. I'm talking about this simply for the sake of like, it's interesting to understand how stream scales and what a consumer needs to do in order to process everything correctly. Because Lambda is a managed service and it's awesome, it actually hides away a lot of this, which I'll talk about. And if you still have a question after that slide, then we can discuss a little bit more. So with all that in mind, there's a lot of requirements. I just put some of the ones that are more interesting up here. As the stream scales for most large tables, you need distributed workers. There's no way that all this processing will happen on a single node for a table that's like 100 terabytes, for example. And it must follow the shard lineage. I talked about this to ensure correctness and consistency. And most of the time, it should support checkpointing, which is both the optimization and the correctness guarantee to prevent losing data. What this means is we only keep the records active and readable from streams for 24 hours. So if you have a node that's processing these incoming stream, and it's not checkpointing, and it dies, and another node will come in, and it doesn't know where the processing ended. So the best it can do is start from the very beginning of the stream and start over. But the problem with that is you have a lot of catch-up to do. So in the meantime, you might get more records that come in, and if you don't catch up within that 24-hour window, you would have lost older records. And then that point, if the node fails again, and the new node comes in and starts processing from the beginning, you would have missed like a bunch of records that you didn't process. So it's both like a correctness issue and a performance optimization to ensure that you regularly checkpoint and like record somewhere, like I've processed records up to this point, so that the new node, when it comes back from a failure, it can just pick up where it left off. I will go through Kinesis Client Library, which does this quite well, a little bit, like 3 slides down, and you see what I mean there. And of course, I already talked about partial failure recovery. So there needs to be some logical way of distributing the work among multiple nodes or machines so that each machine is processing a subset of the stream. So I talked about AWS Lambda, a super awesome service. It's really easy and quick to set up. I'm actually going to use AWS Lambda in my demo because it's so easy to showcase something. It's a managed service, which means you get official AWS support. And it's cost efficient. And I say this because the pricing model for DynamoDB Streams is based on a polling model. So you have to go to Streams every time and say, give me some records, give me some records. Some of those polls, if you have a period of inactivity on your table, are going to come back empty and say, there's no changes since the last time you asked me. But you still have to pay for those polls, because every time you ask DynamoDB for a batch of records, it's charged based on the number of calls. Now, the benefit of using Lambda is Lambda only executes your function if there are records. So it effectively hides away the cost of doing those empty polls. So that's why I say it's cost efficient sometimes, depending on your traffic pattern. But if you have a table that only occasionally has writes, then I think most of the time Lambda will come up to be more cost efficient. And of course, built-in monitoring and metrics on CloudWatch with most AWS services. We use Kinesis Client Library sometimes also because, first of all, it already exists. It's open sourced. It's on GitHub. It actually was written originally for the Kinesis stream a few years back. When we released DynamoDB Streams, we simply wrote an adapter because the APIs are so similar. So you can use the same library, just attach the adapter to it, and then consume from DynamoDB Stream as well. It allows for a lot more customization, more control over your code. There's different customers with different requests. So for more advanced customers that want to go beyond what Lambda is able to provide them, one of the most important ones is stateful processing. So how Lambda works, just a quick overview, is Lambda will pull the stream, and if it gets a batch of records, you give it a function. So it'll execute the function on top of the records. So whatever processing you want to do with the records, it'll spin up, execute it, and then spin itself down. There's no stateful transitions between the two. So if you want to save some sort of state across processing, that's not possible with Lambda because it's completely stateless, which is also one of its advantages. But in this case, if you want to do for example, if you just want to do some simple buffering between batches of records, you can't do that in Lambda because you can't actually hold the state anywhere. If you run Kinesis Client Library yourself on EC2 or your own machines, you can definitely do that. And right now, there's a lot of documentation on Kinesis Client Library. So some customers definitely prefer to run it on their own. And one of the other bigger advantages that I've noticed in working with customers is that Lambda currently only supports in-region invocations. So you can only invoke a Lambda function on a stream that's in the same region as that function. Some customers want to do cross-regional calls for different reasons. So in this case, you can run your Kinesis client library in an EC2 instance in like US West, and you can still attach or do cross-regional polling calls to a stream in US East, and that's perfectly fine. You can't do that in Lambda. So that's sort of I got a lot of questions on Lambda versus Kinesis. I would say as a start, most people should just go to Lambda. It's easy to set up. You don't have to understand the code. You don't have to really write code against it. Kinesis client library is definitely for more advanced users, and sometimes if you want to customize.
How about the checkpointing between these two?
It's the same. Yeah, they both perform checkpoints. I'll actually go through the details of KCL because it's really interesting. Lambda, I believe, uses a very similar structure as what KCL does behind the scenes. It's just managed for you. And obviously, they do their own optimizations to make it a better service. But the checkpointing is automatically done for both of these. So I talked about distributing work. How do you actually build a consumer that follows the lineage and distributes work automatically? The central most important concept in KCL and how it consumes a distributed stream is actually a lease table in DynamoDB. So it sort of uses DynamoDB as like the single source of metadata in order to distribute work. So in this case, I didn't draw all the leases out, but what happens is for a table with 2 partitions, each partition has its own lineage of shards from 0 to 4. So there's actually 10 shards available. Only 2 are available for write, but you can read from all 10. What happens is the KCL actually goes in, and when it initializes, it creates a lease table, and it creates like what they call a lease, which means there is work to be done for each single shard. For shorthand, I said lease 0, 0. So what that means is lease for partition 0, shard 0. So technically, this lease table should have 10 entries. So 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, and then 1, 0, 1, 1, etc. It creates all these leases, which are all these entries in the table, for workers to go and read the table so they know, okay, this is all the work I need to do, and I also need to distribute it among the workers available. And then 2 slides down, I will show how that's actually done. So the lease table name in DynamoDB becomes super important. Some customers use the same lease table name, and that becomes really confusing because if you have an application that's consuming from one stream, you want to make sure it has a unique name so all the workers can go to the same table to check for work. If you use the same name for multiple streams, then what's going to happen is different workers for different streams are going to go to the same table and create leases, and it's going to mess things up a lot. So within KCL, they actually make it very clear that for each application that consumes from streams, you need to make sure that it has a unique, what they call an application name. But that name just gets used for the lease table. So taking us very, very quick breather, step back, how this all works and comes together with KCL. You have an application that writes data to a table. So that's the partitions. And all the writes gets recorded in a stream, which is composed of different shards, as I mentioned earlier. And in order to consume from the stream over multiple shards, you probably have multiple nodes doing the work. In this case, I just put 1 worker per node. You can have multiple, but usually it makes sense to have just 1 worker working on 1 node. The representation is a little easier. And these workers read and write from the 1 lease table, single lease table, in order to distribute work. And I'll talk about how in the next slide. Okay, so here is a very quick snapshot of a lease table that we had back in the day. And the first column is a simple lease key. That's just the shard ID. It's unique to each shard. So remember, this gets initialized at the beginning. And then there's an attribute for checkpoint. So if I'm a node and I'm making progress, once in a while, I'll record the record ID as a checkpoint to say, hey, I've processed everything up to this checkpoint. If I die later, and then another node comes up, then I can go to this checkpoint that I saved earlier to start from that point onwards. And then there's a lease counter field. So for each node that's consuming streams, it needs to have some kind of a health check or health monitor. So this is like a heartbeat. So it increments the lease counter to say, hey, I'm alive, I'm working, and I'm processing records actively. And other workers can monitor this field, this lease counter field. And if I don't update this field in a given amount of time, it's configurable, then the other worker knows, okay, you failed a health check, you're probably unresponsive or not working. I'm going to take over the lease instead. To take over the lease, you actually write your worker ID into the lease owner field. So, and this is a conditional write to make sure no two workers grab the same lease at the same time, right? So if I'm worker 1 and I die, and there's 2 other workers, 2 and 3, trying to take over my lease, one of them will win because one of them will take over, and the conditional write will go through. And then finally, to keep track of lineage, remember I said the consumer has to consume the records in a given lineage. Each shard actually has a parent shard ID that's recorded in the table. So that if I'm a worker and I start working on the first shard, I don't know if I can start working on it yet because earlier shards, like my parent shards, may not have been processed by the application. So you don't want to process later records before earlier records have been completely processed. So I can use the parent shard ID, go into the table, check for the parent shard ID to see, hey, is my parent shard processing completed? And if it's completed, the checkpoint field will actually say shard end. So that's how I know that's completed. Once I see it's completed, then I can start processing the current shard. So that's how KCL keeps track of the processing. So this lease table becomes so important because it becomes a single source of read and write in order to keep track of which work are being done and which workers are alive. And there's a ton of tunable configurations within KCL to optimize for performance. For instance, how long is the health check period? How long do I wait until I take over a lease and assume another worker is basically non-responsive or dead? How long do I wait between polling the parent shard to see if the parent processing is done? If I poll too frequently, it might take up too much, CPU time unnecessarily. If I'm always asking, are you done? Are you done? How long should I wait between empty polls when I'm asking the stream service if there are new records? Right? The more I poll, arguably the more I pay, because there's a lot of cost associated with asking streams for new records. So luckily, KCL is a really well-studied library. A lot of people use it both for Kinesis and DynamoDB. So the official documentation and the open source community has a lot of sort of best practices and just user experience that's available on the internet. Again, AWS Lambda is awesome because you don't have to worry about any of this. No checkpointing table, no distributing work. AWS Lambda handles all that for you. All you have to give Lambda is a function, is your code, like what you want to do with the record. And then it'll just spin up, internally some service that runs your code based on these records. It'll checkpoint it for you to make sure that you don't lose records. It's fully managed, a lot of metrics. And in the demo later, I'll actually show you the CloudWatch metrics and logs. Okay. So that was a lot of information. Any questions before I move on to the demo? Awesome. If you have questions later, feel free to stop me after the presentation. We can chat offline if you think your question is very advanced and don't want to take up sort of presentation time. So a bit of a spoiler earlier, but I'm going to show cross-region replication as the application because it's a very straightforward application to demo using DynamoDB Streams and Lambda. A very quick overview just to make sure everybody's on the same page of what I'm doing here. So there are writes that happen to DynamoDB in US East 1, and we're going to turn on streams on that table. And that's recording the writes. Now using a consumer, in my case I'm going to use Lambda, but you could use KCL or some other open source consumer to basically replicate the writes. Now, on the open source library, we actually, as the DynamoDB team, we actually wrote our own library on top of KCL, uses KCL to replicate as well. And that's just to provide like another example of how we could use KCL to do something like this. And some people want to do like only replicate certain records, so there's filtering, delayed replica, so you delay for a certain period of time before you replicate to prevent against logical corruption. So it's nice to have something open source that you can read and look at. So right now we're actually in the process of refactoring that library to make it look cleaner, update the documentation. So by next week it should be up and updated on GitHub. There is an existing version on GitHub that's a little more cluttered, but just to let everybody know that that's available. In my case, I'm only going to replicate to one other table. In this case, it's showing, hey, after you have the records, you can replay the changes on both tables, and then you get an exact replica for real time. Before I go to the Lambda function itself, here is what I consider to be sort of the heavy lifting part of the function. You're going to see this later too, but I wanted to put it on the slide. So I have the records in a buffer, so a for loop around the buffer. For every single record in the buffer, I get the old image and the new image. And what I do is I just figure out what type of request I need to send based on the images. Obviously, there's some validation that's done in the images to make sure everything's legal. But if the old image is valid, but the new image is not, that means I have an old image, but I don't have a new image. So that change is a delete item. So that's what the first if does. Apply the delete item change on the key. Now, if in the other case, else if the new image is valid, that means that's either an update or an insert. But since we have the entire image already, we don't really care. We can just clobber the existing item. If it's an update, it'll just replace it. If it's a put, then it'll insert it. So we just do put item in that case for both operations. It's a bit of an optimization. Else, error if we don't recognize what kind of operation we need to do. And then there's some management of like how many in-flight requests do I have so I can keep track of. I'll show this a little bit later.
Where's validate coming from? Is that just your custom code?
You see it in the actual function. This is a code snippet. So like validate, I wrote myself. Yeah.
I have a question about the way your string writes to the table. So every time you put a new record, you will scan the replica table for putting that record to see if the record already exists.
No, it doesn't do that. No, it's just every time a change happens, the node, our storage backend that processes that change, publishes that change directly to Streams. So if you insert a new item, it'll just publish a change log to Streams to say, item inserted, here's the item. And if you updated an item, when it updates the item, it has the old image. So it'll publish the old image, and then after it updates, it'll publish the new image in the same record.
When that record is to be written to the replica table,
Mm-hmm.
is it going to scan the replica table to see whether it's an
Update or, yeah, so that's the optimization I talked about. In this case, we don't care because you have the new image. So it'll end up being here at some point. So we just put the entire thing in. You could take the old and the new and then do it in a conditional, right? If you're doing some sort of fancy. In this case, because it's so simple, we're just copying the record as is. We don't need to do update or put. We just put the entire thing in. Because if you only updated a field, it doesn't matter. We have the updated item anyway. So we just clobber everything in the existing. So this becomes complicated if you have like 2 writers and you made like some additional writes to the destination table, and then you clobber everything there, so you lose data. But for the sake of demoing, I thought this was like the simplest way to code it up. Okay, so we can go to the demo. Just gonna quit this. I realized that I can't actually see that very well, so I need to mirror my displays. Good. So we have our demo sort of dev account that we use. I just need to go to DynamoDB to show you guys which table I'm going to use. So I'm in North Virginia. Can you guys see everything? Is that off the screen? Interesting. That's better. Okay, so we're in US East 1, or US East, and I have a bunch of tables. I'm just going to use one of them as a source. I created this one earlier. If you look under items, this is our DynamoDB console, if any of you don't know. I inserted an item. The primary key is ID. I just made up something. And then I inserted an attribute called Daniela. Right now, if you go to Overview, you can see that there is no stream enabled. There was in the past, which is why it shows a stream ARN, but it doesn't matter. The view type is no. So when you create a Lambda function, you can actually let it enable the stream for you. But since we're already here, I want to show you the interface. So you can click on Manage Streams, and it chooses one of the view types. If you want to change the view type after you've enabled it, you have to disable the current one and then enable the new stream. So that's sort of a nuance to be careful. So in this,
Will that change in the future, or do you think that's pretty much the way?
it could change. I don't know, honestly, enough details about the backend to know whether that can dynamically change. I think it might make the management of the streams a little bit more complicated. So I'm going to go ahead and choose new and old images and enable it. And it's just, you see this spinning. It'll take maybe a few seconds. It's in updating mode. So if I refresh and scroll down, still updating. While that's happening, I will go and create a new table, my destination table. Which region? Let's just do Northern California. I work in Palo Alto, so I use this region a lot. So there's nothing in here. So we would create a table. We'll call it demo replica. The partition ID obviously has to be the same because you're replicating the same items. So ID, I think it was a string. Yeah, it was a string. Okay. And then use default settings. Oh, this is so annoying. Create. Okay, so now that's been created. I don't need to turn on streams on my destination table unless I want a daisy chain. So I'm just going to leave it. This one should be done now. Yeah, so you see it's active. And if we go back to click on it, you see that it's enabled, and it has the new and old images. This one should be done now, so we'll close it. Yeah, so now the demo replica is also active. So we'll go to our Lambda console, make sure it's in the same region, North Virginia, as my source table in North Virginia called query test. I actually wrote the function earlier to test it, but for the sake of the demo, I'm going to copy the code and create a new function. Make sure that this is not enabled. Yeah, so it's disabled. Cool. So let's pretend we're creating a new Lambda function. So Lambda actually creates a bunch of really helpful blueprints for you to get started. In this case, I wrote my own code, so I don't need it. But there's one on like process stream, so you can have like a very basic boiler template of how to process records from a stream. I can skip this step. And then my function name, let's say Meetup demo, description, replicates data across regions. Runtime, so you can actually write code in Java, Node.js, and Python right now. I think there are more language support coming later. I just wrote it in Node.js because when it first launched, it was just Node.js, so I started using it for Lambda more, but could have done it in anything. Oh, and also it's nicer to use Node.js or Python because they provide this inline support. If you choose Java, you have to upload like a zip with your files, which I like the inline support. So in this function, it automatically includes a custom library, which is the AWS SDK, since you're on AWS, and then the native libraries for Node.js. But if you need custom libraries, then you have to write it and package it up as a zip and then upload it. In this case, I'm doing something so simple that I don't need anything other than the SDK. So I'm pasting my code here. Want to walk through it a little bit. It does a bunch of setup. I actually timed it just so that the logs show something interesting. A bunch of sort of just configurations I was making earlier. Here's the important part, destination region and table I'm writing to. So I'm writing to North California, so that's US West 1. And my table name, what would I call it? Demo replica. Got it. Oops. Demo replica. So this sets up the SDK, the region, and it initializes the DynamoDB client. This part does some very basic logging. This one actually takes all the records and buffers it. And then handle response, this is the callback function for Node.js. It just says what happens after the requests are finished. It either logs the error, if there was an error, or if it succeeded. I actually keep track of the number of in-flight requests I have so that when it goes to 0, meaning I've processed all the requests and they've all completed, I can actually call context succeed. what context succeeds happens in Lambda. A means in Lambda is you're saying, okay, I'm done processing, shut down my Lambda function, everything succeeded. And I then print out something in the log so I can see how many records because remember, like, you're getting like batches of records from Lambda. So you could get like 100, and you want to make sure you processed all 100 before you end the function. So this is the snippet that you saw earlier on the slide. Exactly the same. I literally just copied it, and I'm incrementing the counter to make sure I'm keeping track. And then validate is down here. I just validate whether the image is actually defined. Yeah?
The rights units in the replica table should be the same as the original table?
The what?
The rights units.
The write units. Oh, it should at least be the at least be the same, right? Because if you want to keep the input and output this, if you're doing other operations on it, you might have to provision more. Sometimes if you want like to self-throttle a little bit, it might be okay to have like 80% of it. The danger is if you have that like indefinitely, obviously you're going to fall behind, right, in your replication process. So that's like the good thing is with that you just monitor it in the console, like you monitor what the latency is. Yeah. Oh, no. So streams right now is for data plane operations only. Yeah. Control plane, I think you can use CloudTrails to audit the control plane operations. And IOPS change would go to update table. Yeah. OK. So validate, pretty simple. I actually want to show the rest of it because it can be a bit tricky. Handler, it's just your file automatically gets called index.js. And handler up here, you can see that, oops, I called like exports handler. So it just matches to make sure which function it's actually running. Role, so this is actually a really important concept inside AWS. Most of you probably know about this. But for Lambda to execute, you actually need to give it some permissions to execute. And that's an IAM role, identity access management. So what that means is you have to create like a user kind of like a role, and then you have to attach a policy to it. And the policy has to say, I'm allowed to use these operations, and I'm not allowed to do this and this. So I want to go through that. So you can use an existing role. I prefer creating a new one just to show people what was happening. So there's templates again. You can create one based on DynamoDB event stream. And then if you click on it, it actually brings you to the console for IAM, which is really nice. In most cases, if you read like security principles, you want to give the minimum, the least privileged principles. So in cross-region replication, what you need to give the privilege is technically reading from the source table stream and writing to so put item, delete item, update item to the destination table. And that's all you want to keep the policy privileges to. In this case, I'm just going to do like resource star just for the sake of time. So here you have Lambda DynamoDB Streams role. That's the name they give to the default role. And then you can create a policy. So here's a policy I used before. We can take a look at it. So it allows a Lambda invoke function. That's important. You need to be given privileges to do that. And then it allows a bunch of actions: get records, get shard iterator, describe stream. Those three are all stream related. And then there's list streams. There's also logs, because the Lambda function is going to be publishing logs to CloudWatch. And then a bunch of other, update table, put item, update item, delete item. With the resource, like I said, you should really only limit it to the 2 tables. In this case, let's just, for the sake of time, just allow it. OK, so now we have a role. A bunch of these tunable parameters. In this case, I don't think we need to touch it. But yeah, VPC support, you can tune a bunch of things. And then we can review everything. Looks good. Create function. OK, so the function's created. But if you notice, what we haven't done is actually tell it which stream to read from. So that's actually an event source. So you can actually attach multiple event sources if you want to replicate multiple tables. But in this case, I'm just going to click on Add Event Source. Event source type is a DynamoDB stream. So you choose the table. My event source is query test. So let's scroll down to query test. Batch size. So the maximum is 1,000, I believe. Minimum is 1. So this batch size is just going to DynamoDB Streams and asking, give me a batch up to this size. So if you ask for 100, you're not going to get 100. You might get 1 if there's 1 available. So it'll return as long as there's something. The default is 100, so we'll leave it there. Starting position, trim horizon, latest. So what this means is start at the beginning of the stream or start from now. Like start from everything from this point onwards. We'll start from the beginning. It doesn't matter. I haven't written to the table anyway. It just reminds you to add DynamoDB permissions to your role, which I did, so that's good. Enable it, submit. Okay, so now it's enabled, and no records processed. So,
in addition to batch size, is there a way to get more specific, like if you want to split your stream based on like a key value or something? I'm just thinking of, like I work a lot with genomics data,
Mhm.
so let's say you were only updating, you're making updates to attributes that were associated with like the key chromosome 1, rather than all the chromosomes.
Mhm.
Could you basically do like a
Filter,
functional
something like that?
Yeah,
Mhm.
exactly, based on like key.
Yeah, right now that's not supported. I know it's a big customer ask, so they're working on sort of like almost like tagging the record to say, hey, it's for this key. And then in the Lambda function, you can say, I only want to process this key. So you give it the ones that you want to process, and the function would then be specifically. So what happens behind the scenes is that it only invoke the Lambda function if it's that record. And that's sort of tagging / filtering. Probably an upcoming feature. I don't have like roadmap or anything. But a big customer asked, so good question. So it should be active now. Here's the monitoring I was talking about earlier. You can see invocations, duration, errors, throttles. If you click on it, it actually just brings you to the CloudWatch console, which has the full set of data. Or you can say view logs in CloudWatch, and it shows you the logs. Let's play with this first, though. So this is my source table, US East 1. And then I can actually edit this to say Daniela, let's say my last name, Miao. Save. So it should actually replicate the entire thing over. So here's my replica in North California. Bring up the items. There we go. So because it's doing a put item, even though this had nothing in it before, it just copied the entire stream. I've actually tried to get it to work such that I want to see if I can beat the replication time, but it's actually so fast that I couldn't. But we can put alias DYM. That's my alias at Amazon. And I'm going to try to refresh that one as soon as possible. So I can save, go over, refresh. Oh, it's already there. Yeah, so it seems to be really, really fast. Probably also because going from US East to US West is only across the continent. Might be a little bit slower from US East to like Sydney, but it's pretty cool, and we can try like a few things. Like I can create an item and say like blah blah, and then I can even add like a different attribute. So hello, oops, whatever, typo, save. So that adds an item, and then if I refresh, it shows up, yeah. So that was pretty simple for a function. I can delete it. And then over here, it's deleted. Yeah, so I've never really been able to like manually beat the check across. And this scan is actually eventually consistent. So, but here, let's go back to the monitoring just to take a quick look. If we like, I don't know if this refreshes it. So you can see it's been invoked twice. There's a bunch of metrics with regards to like how long it took. If you click on logs, where's my log group? So if there's, sometimes the CloudWatch can, because it's eventually consistent, only publishes periodically, can take a little bit before it shows up. Other times, if there's no error, it actually doesn't show up for a long time. I'm guessing what happens with Lambda is that it only flushes the logs if there's an error. and so it wants you to see it right away. And if everything is going successfully, they only flush it periodically. But if there was an error here, you'd see like an error spike. So it's pretty cool. And then you can change the code. And what else? Oh, so in debug mode, you can actually turn off. You can just click on it and disable it. Once you disable it, I didn't actually yet, you can actually test the code. And in configure test event, you can create your own like sample record to see like, oh, what happens if I try to do this? And then you can use a template. I think there's a DynamoDB one. Where is it? There used to be a Dynamo. Oh, there we go. It's up here. Oh, there we go. Sorry, I can't see anything. Okay, so if you choose the template, that it gives you like a really nice, basically a sample record. So if you save and test, I actually wonder what happens in this time. Oh, I think down here it'll say something. And if you go to error, no error, interesting. Yeah, so I mean, things to play with, anything.
So can you do bidirectional then?
So you can set up a Lambda function and then another one, and then do it across. But what happens is, if you're writing the same item and there's no like infinite loop, then that's okay. But if you think about it, the write will get propagated to the destination table. And then what it'll do is it'll actually propagate that same write over back, because you have Lambda functions going both way. But in this case, with cross-region replication, it's okay, because if you write the same item and it doesn't actually change the item, then you don't see an event log. So DynamoDB Stream is not, does not record no ops, where there's basically no operation done. So it'll propagate once to the destination table. The destination table will try to propagate it back. It'll be a no op, and it'll stop there. But if you're like saying, like if you're like incrementing something and you're updating, and
If you wanted to take orders from west, east, and you have unique IDs, but you want to have the data from both environments, so if west went away,
so you're saying no conflicts, for example, append only?
yeah.
Append only would work in this case. But the thing is, the function itself doesn't do that validation for you.
Right, no.
So your application would have to do the bidirectional. Okay, I mean, that's the end of the demo. I'm hoping to publish this template as a blueprint, but they have various constraints. So I'm in the process of dealing with it. But hopefully it'll show up as a blueprint. So you can actually, when you create a function, you can see it. But this is just something I wrote up quickly for this presentation. So, cool. Thank you very much.